We want to find the Taylor series for f of x equals 3x squared minus x plus 7 centered at 0. So we're going to start by finding f of 0. So f of 0 equals 7. And then we'll find f prime of x is 6x minus 1. F prime of 0 equals negative 1. Second derivative of f is 6, and f double prime of 0 equals 6. And then we find that the third derivative of f gives 0, and f triple prime of 0 is 0. And of course, once we get to a derivative that's 0, it's going to be 0. So the kth derivative of f for all k greater than or equal to 3 is going to be 0. And if we find the derivative of any of those kth derivatives at 0, we'll get 0 for k greater than or equal to 3. So our Taylor series, and in this case it's a Maclaurin series because we're centered at 0, is 7 plus negative 1 times x minus 0 plus 6 divided by 2 factorial times x minus 0 squared plus, and then 0 plus 0, and so on. So our series converges for all x. So our interval of convergence is negative infinity to infinity. And I'll leave you to determine why the series does converge for all x. But what you'll notice is that when we simplify this, we get back 7 minus x plus 3x squared, which is the polynomial we started with. We want to find the Taylor series for 3x squared minus x plus 7 centered at negative 4. So again, we start by finding f of negative 4, which is 59. We find f prime of x is 6x minus 1. F prime of negative 4 is negative 25. F double prime of x is 6, and the second derivative at negative 4 is 6. And then, just like in our last example, this is the same polynomial, but set at a different point. Any kth derivative is going to be 0 for k greater than or equal to 3. So at the point negative 4, and at any of those kth derivatives, we also get 0. Again, if k is greater than or equal to 3. So our Taylor series is 59 plus negative 25 times x minus negative 4 plus 6 divided by 2 factorial times x minus negative 4 squared, and then we get our 0 terms. So again, this converges for all x, so our interval of convergence is negative infinity to infinity. And when we simplify our expression, we get 59 minus 25 times x plus 4 plus 3 times x plus 4 squared. We want to find the Taylor series for f of x equals e to the x centered at 0. And again, we're centered at 0, so this is going to be a Maclaurin series. So first we find f of 0 is e to the 0, which is 1. Our first derivative, f of x, is e to the x, and f prime of 0 is e to the 0, which is again 1. And you should notice that any kth derivative of x is going to be e to the x for k greater than or equal to 0, and at the point 0 in any of those kth derivatives we get 1 for k is greater than or equal to 0. So that means that when we start writing out our Taylor series, we get 1 plus 1 times x minus 0 plus 1 divided by 2 factorial times x minus 0 squared plus 1 divided by 3 factorial times x minus 0 cubed, and so on. So when you look at these terms, we find that we're getting the series from k equals 0 to infinity of 1 divided by k factorial times x to the k. So now we need to determine what our interval of convergence is. So let's consider the series k equals 0 to infinity of the absolute value of x to the k divided by k factorial. And we're going to use the ratio test. So we find the limit as k goes to infinity of the absolute value of x to the k plus 1 divided by k plus 1 factorial divided by the absolute value of x to the k divided by k factorial. So we get the limit as k goes to infinity of the absolute value of x times k factorial divided by k plus 1 factorial, and k factorial divided by k plus 1 factorial is just 1 divided by k plus 1, and this absolute value of x can be moved out in front of the limit, so we get the absolute value of x times the limit as k goes to infinity of 1 divided by k plus 1. That limit is going to be 0, so we get 0. So since 0 is less than 1, by the ratio test our series converges for all x. We want to find the Taylor series for f of x equals e to the 3x centered at 0. And again, this is going to be a Maclaurin series. So first we find f of 0 is 1. The first derivative of f is 3e to the 3x. F prime of 0 equals 3. Second derivative is 3 times 3e to the 3x. F double prime of 0 is 3 squared. The third derivative of f is 3 times 3 times 3e to the 3x, and the third derivative at 0 is 3 cubed. So what we're finding is that the kth derivative of f is 3 to the k times e to the 3x, and the kth derivative at 0 is 3 to the k for k is greater than or equal to 0. So putting this together into our series, we have 1 plus 3 times x minus 0 plus 3 squared divided by 2 factorial times x minus 0 squared plus 3 cubed divided by 3 factorial times x minus 0 cubed, and so on. So our series is the series from k equals 0 to infinity of 3 to the k divided by k factorial times x to the k. To find our interval of convergence, we're again going to consider the series k equals 0 to infinity of the absolute value of 3k times x to the k divided by k factorial, and use the ratio test. So we find the limit as k goes to infinity of the absolute value of 3 to the k plus 1 times x to the k plus 1 divided by k plus 1 factorial divided by the absolute value of 3 to the k times x to the k divided by k factorial. And this is going to simplify to the limit as k goes to infinity of the absolute value of x times the absolute value of 3 times 1 over k plus 1. So we can pull our absolute value of x and 3 in front of the limit so that we have the absolute value of x times 3 times the limit as k goes to infinity of 1 over k plus 1, and that equals 0, which is less than 1, so we converge for all x, and our interval of convergence is negative infinity to infinity. We can also note that if we know that e to the x equals the series from k equals 0 to infinity of x to the k divided by k factorial, and we're assuming the series of e to the x converges to e to the x on the interval of convergence, then we can use the properties of power series to get that e to the 3x equals the series from k equals 0 to infinity of 3x to the k divided by k factorial, which can be rewritten as series from k equals 0 to infinity of 3 to the k x to the k divided by k factorial. We want to find the Taylor series for f of x equals the square root of x centered at 9. So first we're going to find f of 9, and that's 3. Then we're going to find f prime of x, which is 1/2 x to the negative 1/2. F prime of 9 is 1/2 times 1/3. The second derivative of x is 1/2 times negative 1/2 times x to the negative 3/2. So the second derivative at 9 is 1/2 times negative 1/2 times 1 divided by 3 cubed. The third derivative is 1/2 times negative 1/2 times negative 3/2 times x to the negative 5/2. And the third derivative at 9 is 1/2 times negative 1/2 times negative 3/2 times 1 divided by 3 to the 5th. The fourth derivative is 1/2 times negative 1/2 times negative 3/2 times negative 5/2 times x to the negative 7/2. And the fourth derivative at 9 is 1/2 times negative 1/2 times negative 3/2 times 1 divided by 3 to the 7th. So writing out our Taylor series, we have 3 plus 1/2 times 1/3 times x minus 9 plus 1/2 times negative 1/2 times 1 divided by 3 cubed divided by 2 factorial times x minus 9 squared plus 1/2 times negative 1/2 times negative 3/2 times 1 divided by 3 to the 5th divided by 3 factorial times x minus 9 cubed, and so on. So we're looking for a pattern here. So when we looked at the second derivative at 9, we had 1/2 times negative 1/2 times 1 divided by 3 to the 3rd. So this is negative 1 times 1/2 squared times 3 to the negative 3. The third derivative at 9 was 1/2 times negative 1/2 times negative 3/2 times 1 divided by 3 to the 5th. So that's negative 1 squared times 1/2 cubed times 3 to the negative 5th times 3. And the fourth derivative at 9 is 1/2 times negative 1/2 times negative 3/2 times negative 5/2 times 1 divided by 3 to the 7th. And that is negative 1 cubed times 1/2 to the 4th times 3 to the negative 7 times 3 times 5. So it's looking like the kth derivative at 9 is equal to 1/2 times negative 1/2 times negative 3/2 and so on, up to negative the quantity 2k minus 3 divided by 2 times 1 divided by 3 to the 2 times k minus 1. And this will simplify to negative 1 to the k minus 1 times 1/2 to the k times 3 to the 1 minus 2k times 1 times 3, etc., up to 2k minus 3. So our Taylor series then is 3 plus 1/2 times 1/3 times x minus 9 plus the series k equals 2 to infinity of negative 1 to the k minus 1 times 3 to the 1 minus 2k times 1 times 3 times 5, etc., up to 2k minus 3 divided by 2 to the k times k factorial times x minus 9 to the k. Now we want to find the Taylor series for f of x equals 1 plus x to the p centered at 0 when p does not equal 0. So first we find f of 0, and that will be 1 to the p, and 1 to any power is 1. Then we find f prime of x, which is p times 1 plus x to the p minus 1. Second derivative is p times p minus 1 times 1 plus x to the p minus 2. The third derivative is p times p minus 1 times p minus 2 times 1 plus x to the p minus 3. The kth derivative of f is p times p minus 1 times p minus 2 all the way up to p minus k plus 1 times 1 plus x to the p minus k. When we find the derivative at 0, we find that the first derivative is just p. The second derivative at 0 is p times p minus 1. Third derivative at 0 is p times p minus 1 times p minus 2. So the kth derivative at 0 is going to be p times p minus 1 times p minus 2, and so on, all the way up to p minus k plus 1. And this is for k is greater than or equal to 1. So given this information, we can start to write our Taylor series. We have 1 plus p times x plus p times p minus 1 divided by 2 factorial x squared plus p times p minus 1 times p minus 2 divided by 3 factorial times x cubed, and so on. So looking at this, we're going to note that if p is a positive integer, then p times p minus 1 times p minus 2 times p minus 3 and so on, all the way up to p minus k plus 1 is going to equal 0 for k greater than or equal to p plus 1. Because at some point, one of these terms will equal 0. And then we would get 1 plus x to the p is 1 plus px plus p times p minus 1 divided by 2 factorial x squared, and so on up to the pth term, which is p times p minus 1 times p minus 2 up to 2 times 1 divided by p factorial times x to the p, and then everything after that is 0. So we're getting a polynomial, and this brings us to a definition called binomial coefficients. So what a binomial coefficient is, for a real number p and integer k is greater than or equal to 1, then we have the notation p choose k equals p times p minus 1 times p minus 2 and so on up to p minus k plus 1 divided by k factorial, and p choose 0 equals 1. So this means that we can rewrite this polynomial we just got using this binomial coefficient notation. So we can now rewrite this as p choose 0 plus p choose 1 times x plus p choose 2 times x squared, and so on. And this equals the series from k equals 0 to infinity of p choose k times x to the k. And this is with the condition that p is a positive integer. And this result is important because it's a special type of series called a binomial series. So for binomial series, if we have a real number, so p is a real number and p does not equal 0, then the Taylor series f of x equals 1 plus x to the p centered at 0 is the binomial series, which is the series from k equals 0 to infinity of p choose k times x to the k equals the series k equals 0 to infinity of p times p minus 1 times p minus 2 all the way up to p minus k plus 1 divided by k factorial times x to the k. So remember, this is just our binomial coefficient. And this series converges for the absolute value of x is less than 1, and possibly at the endpoints, depending on p. we should note that if p is a non-negative integer, then the series terminates and it results in a polynomial of degree p. So to show our convergence, we're going to use the ratio test on this series k equals 0 to infinity of the absolute value of p choose k times x to the k. So using the ratio test, we have the limit as k goes to infinity of the absolute value of x to the k plus 1 times p minus 1 times p minus 2, etc., up to p minus k plus 1 times p minus k divided by k plus 1 factorial. And that's all being divided by the absolute value of x to the k times p minus 1 times p minus 2, and so on, up to p minus k plus 1 divided by k factorial. So this is going to leave us with the absolute value of x times the limit as k goes to infinity of the absolute value of p minus k divided by k plus 1. And evaluating this, we get the absolute value of x times the absolute value of negative 1, which gives us the absolute value of x. So this tells us that our series converges absolutely when the absolute value of x is less than 1. Using the binomial series, we're going to find the Taylor series for f of x equals 1 plus x to the 3 halves centered at 0. So we're going to use the binomial series with p equals 3 halves. So we have this series from k equals 0 to infinity of 3 halves, choose k, times x to the k. And writing this out, it looks like 1 plus 3 halves, x plus 3 halves times 1 half divided by 2 factorial times x squared plus 3 halves times 1 half times negative 1 half divided by 3 factorial x cubed, and so on. And when we simplify these, we get 1 plus 3 halves x plus 3/8 x squared minus 1/16 x cubed, and so on. And we're going to note that if we looked at 0.96 to the 3 halves, that equals 1 plus negative 0.04 to the 3 halves. So assuming that the series converges to 1 plus x to the 3 halves on our interval of convergence, then we get 1 plus 3 halves times negative 0.04 plus 3/8 times negative 0.04 squared minus 1/16 times negative 0.04 cubed, and so on. We want to find the Taylor series for f of x equals 1 plus x to the negative first centered at 0. So this is a binomial series with p equals negative 1. So we get the series k equals 0 to infinity of negative 1, choose k, times x to the k. And writing out terms, this is 1 minus x plus negative 1 times negative 2 divided by 2 factorial x squared plus negative 1 times negative 2 times negative 3 divided by 3 factorial x cubed plus negative 1 times negative 2 times negative 3 times negative 4 divided by 4 factorial times x to the 4th, and so on. So this is 1 minus x plus x squared minus x cubed plus x to the 4th, and so on. There are also some other ways we could have arrived at our answer. We could have done this using our traditional Taylor series methods. So f of x equals 1 plus x to the negative first, and f of 0 equals 1. F prime of x equals negative 1 times 1 plus x to the negative 2, and f prime of 0 equals negative 1. The second derivative is negative 1 times negative 2 times 1 plus x to negative 3. And the second derivative at 0 is 2. So the pattern we're seeing is that the kth derivative is negative 1 times negative 2 all the way up to times negative k to the 1 plus x to the negative quantity k plus 1, and at 0 the kth derivative is negative 1 to the k times k factorial. So this would give us the series k equals 0 to infinity of negative 1 to the k times k factorial divided by k factorial times x to the k, which is the same as the series k equals 0 to infinity of negative 1 to the k times x to the k. Or we also know that 1 divided by 1 minus x equals the series from k equals 0 to infinity of x to the k. So that means that 1 plus x equals 1 divided by 1 minus negative x. So that gives us the series k equals 0 to infinity of negative x to the k, which is the series k equals 0 to infinity of negative 1 to the k times x to the k.